Hi all, and welcome to my AWS Community Day presentation, Building a Serverless Event-Driven Lakehouse. Before we get started, let me introduce myself. My name is Marat, and I'm a pre-sales consultant at Servian, specializing in data in AWS. I'm a huge fan of AWS, and I love experimenting with the various products and services. I'm also an AWS APN ambassador. Firstly, let's talk about the data needs of our organizations. Organizations want the ability to harvest actionable insights from their data. Organizations are starting to trust what the data is telling them and are learning to build strategies backed by the data, not just gut feel. They want access to tools, products, and services that can support their descriptive, predictive, and prescriptive analytical needs. And finally, they want access to this data in a low cost, low maintenance, and scalable platform. But more importantly, they want access to this data now. They don't want to wait 6 to 12 months to gain their first insight. They want these insights now, and they want to make business critical decisions with current and relevant data. Now that we've discussed some of our organizational needs, I want to highlight several principles that our solution will be incorporating and following. The event-driven principle utilizes events to trigger communication between products and services, as well as triggering processes themselves. This enables us to process data as and when it lands. No daily or intra-daily schedules. This is key to getting data into the hands of our users as quickly and as simply as possible. The serverless first principle prioritizes serverless products over serverful products. To maximize scale and reduce operational overhead, we look to fully manage serverless products such as Lambdas over EC2s. We want to invest in the development of our platform rather than the provisioning and upkeep. The principle of object-based dependencies simplifies dependency management through the use of physical objects instead of the physical processes that load or transform those objects. Managing spiderwebs of dependencies is time-consuming and often confusing. Managing timings of data loads, file lands, and more can at times be some of the most frustrating work we do as data engineers. And finally, configuration-driven development allows us to utilize configuration information or metadata to reduce code duplication and increase delivery velocity. Let's talk through what a typical data platform looks like. On the left, we have our source systems, our databases, files, APIs. On the very right, we have our consumption layer, typically our BI layer. In the middle, we have our data lake. It holds all the company data in the various formats they arrive in, structured, semi-structured, or even unstructured. A data warehouse that holds our governed and structured data and is generally considered the source of truth for our organization. And of course, an advanced analytics layer where insights are derived. This is a typical data platform. If you were to go back 10 or even 5 years, it would look slightly different. Back then, a data warehouse would typically be your source for all company data. However, it was costly to develop and very time consuming. And to be frank, it would only cover a handful of use cases. Today, we'll be focusing on our data lake and our data warehouse. How do we extract, load, and transform our data in this platform? We want the data platform to be feature-rich, but at the same time, we want to maximize the platform for speed. Speed of adding new data, speed of transforming and processing that data within the platform, and extracting those values. Now that we have a sense of what a typical data platform looks like, let's cover off the AWS services we'll be utilizing to build out this new platform. From over 180 products and services to choose from, this exercise can literally be done in 20 different ways. But since we've defined some of our principles going in, we'll be prioritizing some services over others. Let's look at each service in greater detail and discuss the role they'll be playing in our platform. DynamoDB will be used to store our configuration information. DynamoDB is a highly scalable and flexible key value pair database that suits an abundance of use cases. Glue will be our transformation engine, performing the various loads and data transformations within the platform. Glue is a serverless Spark service that is generally inexpensive when used correctly, and it's a perfect service for our new platform. Lambda will play the coordinator role. A lot of times it's easy to use and abuse Lambda and use it for everything under the sun. But we have to remember that just because something works doesn't mean it's the right thing to do. Redshift is our highly scalable parallel data warehouse. It provides us with the power to store, transform, aggregate, and consume petabytes of data via a familiar SQL interface. S3 is our data lake. What can I say to this? There is no more perfect service for this purpose. It's ridiculously resilient and impressively flexible. SQS will be used for our ordered queuing system, and finally, step functions will be our auditing and orchestration service. As you can see, although most of these services are serverless, Amazon Redshift is very much not. It has come a long way since its inception, and day by day the service is improving, and for that reason, I'm sticking with it. Now let's put it all together. This is what our final data pipeline looks like. All our services connected via events and triggers, no schedules, nothing hard-coded. This simple configuration enables a multitude of possibilities that, at the same time, are flexible and extensible. Our initial starting point is here, in our data lake. Whether the data is pushed into our data lake via a CLI command, Kinesis Firehose, or pulled in via a database migration service, it all ends up in our data lake. Once the data file lands, it will trigger a chain of predetermined events that will process that data until it reaches its final resting place. The second event in our data platform is our processing queue. The queue enables us to process events in the order they landed in, something that is very important when trying to build an accurate historical representation of our data. We'll be utilizing first in, first out SQS queues to ensure order preservation. On top of this, SQS exposes various inbuilt retry mechanisms and dead letter queues, all useful when building out a more robust solution. Once a new message lands within our queue, our coordinator Lambda function is triggered. The message is read off the queue and the Lambda function gets to work. The first step is to retrieve the configuration information for the particular data file that has landed. This is done by matching the data lake file location to the configuration information stored within DynamoDB. The configuration itself can be quite simple, as this example indicates, but can be extended to encompass a lot more. As you can see here, we have a unique ID for this configuration. We store our source data object, in this case a file in a particular S3 bucket and prefix. We store our target data object, in this case a Redshift table within a particular schema. And we store our job name that will perform the load from S3 to Redshift. And along with that job name, the job parameters that are needed for the job to function correctly. As you can also see, our source and target keys can store multiple object references. That's because a single configuration can depend on multiple sources. Or, on the other hand, a single configuration can load multiple targets. We do not want to limit ourselves to one-to-one configurations. Once our configuration is retrieved, our Lambda function will proceed on to the next step. Now, in a situation where a configuration was not found, our Lambda function can simply alert our support team. This event can trigger our development team to consider whether creating a new configuration file is necessary, or they can simply ignore it if no further processing is needed. Now that we've retrieved the necessary configuration data, our orchestration service will proceed with running the load job configured. Step functions enables us to create reusable paths and patterns for our various data platform needs without worrying about job durations, custom error handling functionality, and more. Step functions can be in a state of execution for up to a year, with plenty of out-of-the-box functionality and support for some of AWS's most popular services. On top of that, step functions creates immutable logs that can be accessed at any time for auditing and debugging purposes. In this scenario, our step functions will execute our glue job. The glue job will receive the necessary parameters that were stored within our configuration table and proceed with the file load into Redshift. Because glue doesn't have the same timeout limitations as Lambda, it is far better suited for more prolonged running workloads while still keeping to our serverless theme. It is also worth noting Glue isn't just Spark. Several years ago, AWS released Glue Python Shell, which is closely aligned to Lambda, but without the execution duration limitations. In this example, we actually won't need to utilize Spark, as our pipeline will only perform a simple Redshift copy command from S3. Likewise, we can again utilize Glue Python Shell whenever we want to transform data within Redshift itself by simply executing SQL commands and waiting for them to complete. Glue provides a simple, flexible, and cost-efficient service for most of our needs. In those scenarios where data transformation is necessary, Glue Spark can be utilized to transform data directly within our data lake without the need to load the data into Redshift first. When using Glue Spark, however, I suggest the use of Spark SQL, as this will enable us to create configuration-driven Spark jobs that can simply take a SQL statement as an input to do its processing. Without Spark SQL, we'll be forced to build bespoke Glue Spark jobs for every different transformation or load. Once the data is loaded into Redshift, we can stage the data for further transformations up the value chain. We can also historicize the data, enabling point-in-time lookups, and more. Now that the data has been loaded into Redshift, any further transformations of that data should be typically conducted within Redshift itself. We want to utilize the parallel nature and massive scale of Redshift to our advantage. We also want to avoid the costly and time-consuming process of extracting, transforming, and loading the data back into Redshift. In most cases, SQL is powerful enough and flexible enough to perform necessary transformations. After the load into Redshift completes, step functions will perform the next step in our event-driven pipeline. It will publish a new message into our processing queue. Remember our configuration data? Well, in there, we specified our source and target objects. These objects enable us to build out our object-based dependency graph. Thanks to this information, we now know which objects were impacted by our data load. This allows us to use that information to trigger the next set of jobs that depended on our target object being loaded. By inserting our target object into our process queue, we enable our platform to retrieve and execute the next set of jobs. This process will continue until the very last target object is loaded and is no longer a dependent object. This is object-based dependencies, and this is how it can be easily modified by introducing more object dependencies, removing object dependencies, or changing the object dependencies within existing jobs. All of this is achieved simply by introducing new configurations that depend on existing objects or by creating new ones. No need to modify orchestration jobs, DAGs, or custom scripts. Now that our pipeline has completed its very first execution, it will continue doing so in the same manner for every execution to come. Simply by changing the configuration and execution of specialized glue jobs, we can cover a multitude of data platform scenarios, including data profiling, data validation, data loading and transformation, extraction, tokenization, and many more. The pipeline I've presented to you today can be thought of as an execution framework that can be extended for the various use cases, all whilst conforming to the same simple pattern. We only need to change the functionality within the glue job to perform the various functions. And if glue is not the right service for your use case, it can be simply exchanged for another. Remember, this pipeline is only a demonstration of what's possible, and I've only run through a single use case. Your usage may vary. In some instances, you could remove the data warehouse entirely and keep everything within your data lake. In other instances, you may substitute the data warehouse for a simpler RDBMS or a NoSQL database, or you can have all three. Before I wrap up, I want to highlight some key takeaways. There'll never be a one size that fits all. There will always be an edge case or two that either can't or are too difficult to solve with an existing solution. It's okay to accept that, and it's okay to build something more bespoke to handle that edge case. At times, it's a lot harder to make an existing solution work with an edge case than it is to build a new solution for that edge case. And finally, there is no best practice. There is simply what's considered good practice today and what will be considered good practice tomorrow. We have to know when to adapt, when to rework, and when to introduce new patterns and solutions so that our solutions can stay relevant and up to date. Thank you for tuning in and watching. I hope you've learned something new today and enjoyed the presentation.